Okay, this is a sample of data. So you guys are going to be doing a lab about acceleration. And let's say you take 5 different times and you want to be like, you want to be really impressive and you want to do uncertainties for your lab. You don't have to do uncertainties. Let's say you want to do them. So you get all these different times. You take the average, so you take the sum and you divide it by the number. So in this case, 5. And Juder got 1.0184. And I got the same. How many other of you got the same? Okay, so it sounds like we're good. That's fine. Now you can use this value, but would you say that the time is exactly this?
No.
How do you know that it's not?
It's just an average.
Right.
How do we know if it is?
How do you know that it is or that it isn't? How do you know this is not the exact value you should use? Can't you just say, no, it's exactly this. It's this many seconds. The reason is because you've measured it 5 times and you got 5 different times, right? You got 5 different data points. So it can't be exactly this. If it was exactly this, then you would have gotten this every time, right?
Yeah.
So we're not sure exactly what the time is. The best we can do is say, it's around here, but it could be in a range. And the range we're gonna say is plus or minus the biggest distance between this and any of these data points.
So which is
Okay, so look at, so which one is the farthest away? Let's find the biggest and the smallest.
1.008 and 1.085.
So this is the smallest, right, Parham? What's the biggest one? This one?
I'm on my back.
So we have the biggest one and the smallest one. Let's find the distance from the biggest one to that average and from the smallest one to the average. So you go 1.025 minus the answer from the last one.
0.017.
So this is going to be, the difference here is 0.0066. Isn't that right?
I got 0.017.
Which one did you minus?
I did the biggest one minus then the smallest one.
Oh yeah, don't do that. Just the biggest minus the average.
Oh.
That's what you want to do. Because sometimes the average is really close to one or the other. In this case, it's going to be pretty similar, but. And then you do the average, 1.01184, and you subtract this number, the smallest, 1.008. And this one we get 0.0104. So they're a little different. Which one is bigger? Yeah. So we're going to use this one. That is our uncertainty. This makes a little more sense if we have more measurements. Like if you have more time, you're going to do this 1,000 times. And then you're going to say, it's around the average, but we know it's within the range from our average to our farthest away data point.
How did you get it to be that number?
This?
Yeah.
I did the average, so this is the average. And then I subtracted the smallest data point. That's how far away this is from that.
So then why did you do it with the biggest one?
Well, just in case. Because it's the largest distance from the average to any of these data points. If we don't want to do all the middle ones, we can just do the biggest one and the smallest one and find the distance away that this
So which one's
average is.
bigger?
Yeah. It's the biggest
Yeah, 'cause you
difference.
wanna find like the uncertainty, like the
Yeah. Yeah. Yeah, exactly. And by the way, is a bigger uncertainty worse? Like, isn't it better to be more precise?
Yeah.
So shouldn't we take the smaller one then?
No.
No.
Here's the truth. It looks better to be more precise, right? If you said, no, this is the time and it's plus or minus 0.0001 seconds. It's like less than a microsecond. We know what we're doing. It's very precise, right? And sometimes you'll get told to do that in chemistry and stuff.
Yeah.
But that's where, if you're using an instrument where you get the same value over and over and over again, like if you measure a volume in a graduated cylinder, you might get exactly 24 millimeters. And you can look at it 100 times, you're still gonna see 24 millimeters. Then you go to the smallest increment of the instrument. So if it might be 24 plus or minus 1 millimeter. Or sometimes people say, well, you can go to the half. But that's only if your measurement is the same every time. This one is going to be plus or minus 0.0104. And so we have a range. We could be this much lower than that, or we could be this much higher than that average. And the reason why a bigger uncertainty is best is because if you're an engineer and you're building a bridge or a building, and you tell the builders there's 24 micrometers of deflection in this steel beam, and they're going to say, is that exact? You say, yes, the beam will deflect exactly 24. And then they build the building, but then it gets on a hot day and the thing's a little bit more bendy, and maybe you get too much flex and the building falls down. That's really bad, right? You should have said it's 24 micrometers plus or minus 5 micrometers, maybe. Depending on, you're going to test that beam a whole bunch of times and you're going to get all these data points. And you're going to say it deflects, this is the average deflection, but it deflected plus or minus whatever the largest amount to whatever data point you get. And that's going to make things safer. In physics, we want to be safe. We don't want to say things we don't know. So that's why you calculate uncertainty. So if you want to do that in your lab, you can do that, and I'll show you how to do the error bars if you're using Logger Pro later.